So let me begin with some scripture here. So I'll begin with some scripture. I'm going to begin with some scripture. This is Romans chapter 12, verse, let's see here, 2. It says the following, "And do not be conformed to this world, but be transformed by the renewing of your mind, so that you may prove what the will of God is, that which is good and acceptable and perfect." So I'll begin with a word of prayer. Heavenly Father, we thank you again for this opportunity we have just to meet and study your creation. Just pray that you'd guide our steps today, help us to understand a little bit more about energy and about how to just solve physical problems with it, Lord. In my prayer, Lord Jesus. Amen. All right, so last time I showed you guys a little bit more about conservation of energy and everything. We proved a theorem last time, right? Basically, our theorem was this. If the net force is minus the gradient of a potential energy function, then the energy, the net mechanical energy, which is equal to 1/2 mv squared plus the potential energy, is conserved. And when we say conserved, we just mean that it's held constant throughout the motion. So of course that can be very useful for solving a variety of problems. I want to give you guys another example of finding, a couple more examples actually, of finding the potential energy function from a given force field. So like, let's see here. I'll start out with a relatively easy one here. So suppose we have the force field is e to the 3x plus y, comma, y cosine of y squared. Wait, did I do this last time? Oh, I did this one. I'm sorry, guys. My bad. We already did this one. I don't want to show you guys a rerun. We did this one. That was the one with the x, y in the answer. Let's try something a little bit more advanced. We did. Like last class. All right, so x over x squared plus y squared plus z squared to the 3/2 power. And the same pattern, but with z over here. All right. So this one's a little bit fussier, but it's physically very interesting because what this is in another notation, this formula you could write. It's basically like r vector divided by r cubed, or if you like, you could say this is r hat divided by r squared. So this is the inverse square force. Its magnitude is inversely proportional to the distance from the origin, and it points radially outward. So in the context of next semester, this would be called the Coulomb field. All right. At the moment, this is the gravitational field of a point mass. If we use Newton's universal law of gravitation and put the point mass at the origin. Now, if I do that, I have to put a minus because, of course, gravity is attractive, right? So yeah, we'd want that. Anyway, this is the problem. Can you find that this is, equal to minus the gradient of some potential function? And so, like, I don't want to get into all the details for you, but if you study the gradient in other coordinate systems, it turns out that the gradient can be written like this: partial r, r hat, partial u, partial r, plus like theta hat times something. The something doesn't matter. Plus phi hat times something. The something doesn't matter. But this right here these have like theta and phi dependence. Now, if you don't know what theta and phi are, these are the spherical coordinates. Just to tell you what these guys are for a second here. If we are in 3 dimensions, this angle is theta. You guys know about that. The angle that drops down here off the positive z-axis is usually called phi. So like the spherical coordinate formulas, well, I'm using r for the radius. In math, we tend to use that rho symbol there, but I just can't do it in physics. It's wrong. Now, if you believe me, we're just trying to solve, let's check it out. We're just trying to solve really minus the gradient of phi, right? So minus r hat times partial u partial r is equal to r hat over r squared. All right? Like that, if you just look at it, that's what we're trying to solve, because this is a spherically symmetric force field that's got no dependence on the choice of angle. It's the same in all different directions. There should be no theta or phi dependence to the potential. And so really, it's just a calculus 1 problem. If you look at it from this perspective, we're just trying to solve partial u partial r equals to, minus 1 over r squared. So what's that tell us? U is what? Can you anti-differentiate minus 1 over r squared? What would you get? What's that? I just didn't hear it. I heard an r. 1 over r? Right, 1 over r. So that is probably the potential energy for this force field. Now, if I put it back in Cartesian variables, it looks like this. So u of x, y, z is like 1 over the square root of x squared plus y squared plus z squared. There you go. That would be the potential energy for this force field. And you can try it out. If you take the partial derivative of that function, what happens? What happens when you take the partial derivative of this 1 over the square root? Like, check it out. What happens when I take partial u partial x? What goes on? We've got minus 1/2 x squared plus y squared plus z squared. This is the minus 1/2 power. Minus 1/2 minus 1 is minus 3/2. Yes. And then I have to multiply by the derivative of the inside function, because there's a chain rule that we must mind, which gives me a 2x from that. So 2x cancels the 2. What am I left with? I'm left with x divided by x squared plus y squared plus z squared to the 3/2, right? And this calculation checks that I'm not wrong, right? Like, you could view all of this spherical stuff as kind of just hand-waving, if you like, in here. It can be derived rigorously. But that gave us a good guess for what the potential was, namely 1 over r, and then I write down the guess, and now we can partial differentiate it and see that, in fact, if I take the partial derivative with respect to x, I get exactly the x component like I need, right? Assuming I put the minus here, right? Oh, hold on a second. You guys sold me a bill of goods. Yes? Are you about to tell me I'm off by minus?
I was about to ask what happens to that minus 1 there, because there was a minus 1 there, so it shouldn't be.
Well, yeah, exactly. So there is a minus there. In this calculation, there's a minus. And what does that mean? If I differentiate 1 over r, what do I get? No. Differentiate 1 over r. Minus 1 over r squared.
You mean negative of 1 over 2r squared? Or, no, is it just
Wait a minute. That's not a problem. I mean, that's what I want, isn't it? That should be okay. Oh, I'm a dummy. Look, so the force is minus the gradient, right? I've got minus from the partial derivative. Then what happens? we put the minus in the definition of potential energy there as it relates to the force. So, you know, when I calculate F equals minus the gradient of U, then I get minus that minus, I get the X over, you know, X squared plus Y squared plus Z squared. Sorry, so that minus and this minus combine together to get us the plus that we need. And the calculation goes the same for Y and Z, right? There's a symmetry here between the way X appears in the formula and the way Y appears in the formula. So if it works out for X, it's going to work out for Y and Z just the same. Any questions? So this one, I discovered the potential energy by what? By guessing, right? A little bit different than what we've done before. Oh, lest I forget. If you could add a day for me. Uh-huh.
You said those don't matter because since it's a force field, that forces no matter what.
Well, I'm telling you, like in general, if you have a function of r, theta, and phi, there could be terms that appear over here. Now, I have not even defined for you what theta hat and phi hat mean. So, like, I don't really want to talk about those in here. If you want me to tell you more about them, I can talk to you about it after class or something. But what they are is they're unit vectors that point in the direction of increasing, you know, theta or increasing phi. I mean, I can show you a picture of it if you want, but yeah.
So just to confirm, the r hat comes from the unit vector formula?
Yeah, r hat, what r hat means, it is a unit vector that points in the direction of increasing r. So it's just the spherically outward pointing unit vector. Let's see here. Maybe I can demystify. So in like 2 dimensions, no, I don't want to get into that. Hold on a second. No. I'm going to stop. Example 2. Let's see here. We could look at this force field. So guys, the reason I switched to spherical coordinates there is just to like kind of show you another way of thinking. If you want to know more like details about how to calculate with spherical coordinates, I'm happy to tell you about that like in office hours or something. There's a lot more I can tell you, but I probably shouldn't say it here at the moment. So here's another force field. This is kind of the analog, in some sense analogous to the other one, because this in 2 dimensions, this is essentially, what's the magnitude of F here?
It'd be the square root of x over x squared plus y squared plus y over x squared plus y squared.
Okay, so what you're telling me is 1 over the square root of x squared plus y squared, right? The dimensions here, each component of this vector has dimensions like length over length squared. So the magnitude should be like 1 over length. So my claim is consistent with dimensions. But you can work it out, it's that. All right, so question, we want to solve this partial u, partial x equals to, you know, minus x over x squared plus y squared. I don't think we need any kind of newfangled coordinates here to see through this one. In fact, maybe you guys could have seen through that if we just used Cartesians. But I thought, well, maybe it would be interesting to look at spherical coordinates for a second, so I did. But can you guys see what the formula should be? How about this?
Are we looking for the antiderivative or?
Yeah, like let's try to do them both at once. Let's get a 2 for u equals to what? We're trying to find u. We've got partial u partial x is minus x over x squared plus y squared, and partial u partial y is minus y over x squared plus y squared. So yeah, we want to anti-differentiate. But when I say, what I really would like you to do is just kind of guess. Try to guess. Yeah.
Negative.
A negative? Okay. I like that.
1/2 natural log of x squared plus y squared.
I got a 1/2. I like that. Natural log of x squared plus y squared.
How close am
I think that's going to work. If you differentiate that, what happens? Think about it. When we differentiate the natural log, it does the reciprocal of the argument, which is 1/1 plus x squared plus 1/x squared plus y squared. And then the chain rule either pulls out a 2x or a 2y, depending on whether we're doing the x or the y derivative. So yeah, that's exactly it. We have a winner. There you go. So listen, I have some of these in the homework and so forth. The basic rule of thumb here is to try to anti-differentiate both, make a guess, and then check your work, all right? Which is to say partial differentiate that, multiply by minus, see if you can get back to the force. Yeah?
Could you write that out? If that works. Or just like write out.
I'm suggesting guessing. I can't write out guessing. You know? So my point is that if we take partial x of the natural log of x squared plus y squared, we get 1/x squared plus y squared partial x of x squared plus y squared, which is 2x over x squared plus y squared. Likewise, partial y of the natural log of x squared plus y squared, for almost the same reasons, works out to 2y over x squared plus y squared. But remember, the force, we want it to be equal to minus the gradient of the potential energy, which is going to be minus partial u partial x comma minus partial u partial y. So for us to have guessed correctly, it must be the case that when we partial differentiate our answer with respect to x and partial differentiate our answer with respect to y, multiply those by minus, we should get back to the force field we started with. And that will be the case here. See, because if I differentiate this with respect to x, I get 2x over x squared. Multiplying by minus 1/2 gets me back to, minus x, but the minus and the minus cancel, and I get there, and likewise. If you want me to explain the mechanics of the integration, it's a u substitution. You can think of the denominator as being u. Then you're like, du will be 2x dx in the x integration. It'll be 2y dy in the y integration. So it's a u substitution if you don't see the guess. But okay, so I think I've done enough of these. I'm going to go on, all right? Because we'd actually like to talk a little bit more about some one-dimensional things. And so one important example that we should spend some time on is the case of the spring. So let's talk about the spring. Spring mass system. So the basic story here is we've got a spring, and I draw it like this. My spring and my resistor look a lot alike. And then you've got a mass over here. All right? So I've got my mass, I've got my spring, and the spring has spring constant K. All right? And to keep things simple, no friction. All right? No friction. It's just going back and forth. All right? And Hooke's law tells us that the force, the spring force, is actually equal to minus kx. This is Hooke's law. So the motion's one-dimensional, and so basically the situation here is that somewhere in here, this is x equals to 0, let's say. And so what I'm saying, at the moment, my picture, at the moment, I have the spring stretched out just a little bit. All right, it's stretched out just a little bit. And so what's the situation? If the spring is stretched out just a bit, so this right here is x, okay? This is a picture of x positive, right? In which case the force does what? Goes to the left, right? That makes sense, right? If the spring is stretched out, it tries to restore it back to the equilibrium position, right? So the force would be like this in this situation. And then what happens? The spring pulls back, goes through the equilibrium position, and then does what? Then the spring compresses, right? Then X is negative in the compression, which means the force is now minus a minus, which is positive, which means rightward, right? So the spring pulls the mass that way, and then it pushes it this way. Push, pull, push, pull, push, pull, right? And that's exactly, this is the principal example of what's called simple harmonic motion, or for short, SHM. And I'd just like to work out the mathematics of this for you and to try to analyze what's the energy of a spring, all right? So it's characteristic of the spring constant K as well as the mass M. Okay, so this is one-dimensional. Let's find the potential energy. What should this be equal to? In one dimension, the gradient is just minus du dx, right? No need for any kind of fancy partial derivatives here, just a single ordinary derivative. And then we integrate both sides. And that tells me what? U of x is equal to 1/2 kx squared, right? There you go. That's the standard formulation for the potential energy of spring. Potential energy of the spring is that. So what's the total mechanical energy of the spring? I can't spell. Let me abbreviate. Aha, there we go. Energy of spring is E 1/2 mv squared plus 1/2 kx squared. There you go. That's the total energy of the spring, right? And if that's all that there is, if there's no friction force, energy is conserved, right? So if I know the maximum, there's two different things that will be pretty much telling me everything I need to know. If I know the velocity of the spring as it goes through the equilibrium position, right, that will inform me as to what the maximum, distance it goes from it. Let me put some examples here. So like if when x is equal to 0, you have, let's say, v is equal to 3 meters per second, where, let's say, m is equal to 2 kilograms, and k is equal to, just make up something here, 100 newtons over meters, right? K has to have units of newtons over meters because k times x is a newton, right? So if that's the case, if when x is equal to 0, we have a velocity of 3 meters per second, right? And the mass is 2 kilograms, and the spring constant is 100 newton meters, then the question I can ask is, what's the maximum x? What's the minimum values for x? Can I solve that? I think I can because energy is conserved, right? So the energy at the initial point is equal to 1/2 k, 1/2 mv squared, right? There's no k. 1/2 mv squared. So 1/2, maybe, I don't know, 2 kilograms. 2 kilograms times 3 meters per second squared. You said 18?
Oh wait, I
yeah, you're too generous. So yeah, 9 joules, right? 9 joules is the total energy. But that's conserved because this is a conservative system. So we can say that that's equal to what? Yeah, that's equal to 1/2 k xf squared, right? Supposing that Vf is equal to 0 at x max or x min, right? Does that make sense intuitively? When the spring is most outward stretched or most inwardly compressed, the velocity is 0, right? Okay, so we know what k is, and we can then, now here's your 18. So I've got 18 joules divided by k is equal to xf squared, which tells me that xf is equal to plus or minus the square root of like 18 joules divided by 100 newtons over meters. Now, a joule is a newton meter, and so the newtons cancel, and we're left with a meter squared inside the square root, which is good because that means that the totality of the units here is just meters, which is what we'd like to see. Plus or minus, what we got?
0.42.
All right, I'm going to believe it. 0.426, all right. 0.42, 0.424?
Yes, sir.
Oh, okay, and that would be in meters. So also known as plus or minus 42.4 centimeters. A lot of times these spring problems are packaged in terms of centimeters, all right? Does that make sense? I mean, conservative systems are super interesting because we can bridge different scenarios that we're interested in by just assuming that the total energy is conserved. That's all there is to it for a lot of these. Now, for the spring mass problem, there's actually a much more interesting way of understanding the motion in terms of something called the Poincare or the phase plane. So I'd like to talk to you about that because this is a broader topic. And so we're going to get back to solving these kinds of problems soon, probably next class mostly. We'll do things like inclined planes and all that stuff. We'll be back to that and out of the math here. But I do have one other important mathematical thing to do with you. And it's important because this isn't just this course. This also touches, this is a thing you also will see in like a chemistry course. If you guys were to say go on and take a course in say solid state physics or something like that, this kind of thinking becomes very important. This sort of energy analysis is actually one of the major tools we have for analyzing physical systems. And so the idea is fairly simple. It's based on the observation that energy is conserved. Now, I need to drive a little bit of something here for us. This is one-dimensional. So one-dimensional, what we got? Let's just take a, you know, the net force, if it's conservative, is minus du dx, right? But that's also equal to the mass times the acceleration. All right? So that's what? That's the mass times dv dt. Right? So in other words, in short, what we have, just to get it here, we have dv dt is actually equal to minus 1 over m times du dx, or if you want to, we could look at it as minus the net force divided by the mass. That would be dv dt. On the other hand, this is kind of dumb. We also had the velocity is equal to, well, dx dt. Now, okay, so the energy is a function of x and v. It's what? It's 1/2 mv squared plus the potential energy, which is a function of x. This is constant on motion, for the motion of the system. I could derive that again, but we worked it out already, so let me not belabor that point. But if you were to differentiate E with respect to time, you could show that that's equal to 0 by just using Newton's laws, all right, and the chain rule. Getting to the point here, if I was to plot, all right, if I was to plot here, x versus u, all right, and then right underneath it, I was to plot, all right, here x versus not u, but the velocity, then this is what's called the Poincare, or sometimes the phase plane. And it's a plot of position versus velocity. If we plot position versus velocity, we can understand the totality of different possible scenarios for the motion. All right? And all right, so let's do this for the spring, because the spring is a really nice example, and it's probably the most simple to understand example for all this. And here's how it goes. So, what's the formula for the spring? What do we have? U is what? 1/2 kx squared, right? What's that look like?
Would it be negative 1/2 squared?
No, it would not. It's 1/2 kx squared. You need the minus because Hooke's law's got the minus in it. That's, yeah, but this minus is a plague on me, admittedly, but I'm quite certain it's 1/2 kx squared. That's a parabola, right? We can graph that. We know that, like so. Whee! All right. So there's your potential energy plot. All right. And if I probably should be more careful with my plot. Let me make this a little bit more shallow, just to make my life more interesting, slightly more interesting. So I'm going to try to make this actually symmetric. I don't know. I'm trying, guys. I probably failed, but anyway, so what we're looking at here is potential energy versus position. And I want to show you that if you have the potential energy versus position graph, you can then from that extrapolate what the position versus velocity graph has to be. Now, the way this is done is you pick some representative energy levels. So, and this is a, what's the word? Qualitative. This is a qualitative graph, okay? It's not meant to be quantitative, it's meant to be qualitative. We're going to understand qualitatively what the general possible motions are. And of course it's a spring, so we already know, but that's a good sort of testing ground here. You see that? The intersection of this, let me call this energy level E naught, is here and here. So I just take those and I bring these down like that, all right? And let me do another level in green. Energy level E1 up here. And so that will come down here like so. Pencils are great in this kind of stuff. And then finally, energy level up here, E2. All right. And of course, if you guys got some like graph paper, I guess you don't have to do these dotted lines. You can kind of like, but I find the dotted lines are helpful just to keep me honest. All right, what's going on? Let's think about this. The key idea here is that the energy, total mechanical energy, is the sum of the kinetic energy and the potential energy, right? Question. Can the energy, right? Can the energy be that's not the way to say it. Oh man, sorry guys. Well, sorry, my mind stopped working mid-sentence. The point is here, let me just say it in a different statement. I'm trying to get confused. I'm trying to tell you something wrong, so you have to think a wrong thought. You can't have the situation, let me put it this way. Could you have 1/2 mv squared be negative? No, it's impossible, right? kinetic energy is positive. If kinetic energy is positive, right, that means that for a given energy level, you cannot have, like, it's not possible to be below the potential energy graph. Like, if I could somehow have a motion that was past where I've drawn, then the only way that you could have the sum of the energies be E naught and be like over here would be the case that you actually had a negative kinetic energy. See, because potential energy plus kinetic energy plus potential energy is equal to the energy that's given. So if you're below the potential energy graph, then you'd need negative kinetic energy for that to happen, but that's impossible. So that's why for the given energy level E naught, you're stuck between those two extremes. The motion's bounded there. That's the min-max we explicitly found for the previous example, right? So the graph of the motion, it looks something like this. And in these ovals in the phase plane, the whole story we were just telling about the spring stretching out and going back together are told. So, like, what's going on? If the velocity is positive, which way is the trajectory going? It's going to the right, right? Velocity positive means you're going this way. Velocity negative means you're going to the left. All right? And what's going on is, like, for a given energy, your spring does what? It does what? You can go around this loop and it's the full story of the spring, right? Like, let's start out at point A. What would this be? And then point B, point C, point D. Tell me the story. At point A, the velocity is 0. It's fully stretched out. It's maximally stretched, right? Then, as time goes on, you go to point B. At point B, it's going through the equilibrium position. There we have the max speed to the left. It continues past there to its maximum compression at point C. And see there, the velocity is 0 again when it's maximally compressed. And then what happens? The spring uncompresses and converts the potential energy back into kinetic energy as it goes to point D. Again, at the equilibrium position where x equal to 0, we have maximum velocity in the positive sense. And then, we get back to A. Just like that. So if you can draw the phase plane, you can understand what the possible motions are. What do you think these pictures look like if you've got friction? Spiral is correct. That's exactly it. Energy is not conserved. You can prove that the change in the energy per unit time is equal to the like the coefficient of the velocity dependent friction force. If you just add a friction force that's minus BV, it turns out like dE dt is equal to minus B, and so the energy level drops. And indeed, right, you toggle from like one oval down to a lower one until eventually you just spiral to 0. Because if there's friction, the spring just stops oscillating. It just drains its energy into the friction. Yeah. Anyway, that's beyond this course, so I'm glad you guys knew it, so I don't have to teach it. Cool. So let's see, your next example. Example, what are we on? Goodness gracious. I think I forgot the number. Well, that wasn't an example, that was a discussion. I guess this feels like example 3. So I guess this is example 4. Okay, so I want to point out to you something. When you do these pictures, so like definition, a critical point. What's a critical point? A critical point in this story would have dx dt equals to 0 and dy and dv dt equals to 0. So you have both dx dt being 0 and dv dt being 0. Now dx dt being 0 is what? That's just v equals to 0, right? So like critical points in the phase plane have to happen. They have to happen on the x-axis. where V is equal to 0. But they also have to be such that dV dt is 0. When can dV dt be 0? Well, look at what that is. dV dt, remember, is this. So to have dV dt equal to 0, we would have minus 1 over m du dx equal to 0. Oh, wait a minute. What's du dx equal to 0? That's the condition for a critical point in the sense of calculus 1 for the potential energy graph. Right? What's the critical point for the potential energy graph here? Just the origin, right? That's where du dx is 0. So critical points are where the force is 0, which correspond to points where your potential energy is either minimized or maximized. All right? So an interesting question, the way I usually give this on a test, because in homework I can actually give you a formula and let you like work out the graph and junk. But in the test, usually what I do is I give you a sample potential energy diagram, and I ask you to like come up with the phase plane from it. So let me show you an example kind of like that. So suppose, and I usually ask even a less interesting question than that, but let's suppose the potential energy graph looks something like this. All right? So here's my potential energy graph. All right? And then what I want to do is to maybe draw the corresponding phase diagram down here. So, all right. There are 1, 2, 3 critical points in the potential energy graph. Those will correspond to critical points down here. That either means that these points are going to be what's called an attractor or a repeller. In other words, like either solutions are going to like flow in. Either you're going to have this kind of situation, or we'll have something where, depending on how you gave it a shove, it might either like go away from the point or come towards it. Let's see what happens. All right, so I need to talk about some energies. Let's do this one right here. I'll do this from an E naught. You guys see that one? I'm going to skip the dotted lines because it makes it too busy, I think, on the board. I'm just going to try to do my best. So like here's E naught. So that gives us like a little loop like that there. See that? Because if you have energy E naught, you're going to be stuck in this little loop here, basically going back and forth in this what's called potential well. You can't get past these 2 points, because to get past those 2 points would mean that you had negative kinetic energy, which is impossible. Then what happens? Over here, we've got something more interesting going on. Maybe we got something like this. Now, the deal is the trajectories always flow to the right for positive V, and they always flow to the left for negative V. So that's kind of something to think about. So question. I can now ask you a physical question. If your particle has energy E naught, where does it go? Describe its motion in the situation of example 4. Can you tell me what happens? Again, suppose your particle has energy E naught. Where does it go? Yeah.
At one point it's going to go back and forth on the left one. I don't know how to describe the right one. Semicircle.
Right idea. It's a trick question. The answer is you can't say unless I tell you where the particle is. So there's 2 situations. The one situation is that its initial condition puts it here. If its initial position is like here, then it's just going to oscillate back and forth in simple harmonic motion near this potential well as it goes around this loop. On the other hand, if the initial condition puts it somewhere over here, what happens is it comes in from wherever it was, it gets to this minimum point of approach, and then it gets repulsed back away out to infinity. It never comes back. It's not a, just basically bounces off the potential well. So in the picture, the motion would look like this. Comes in, goes out. All right?
It seems like an oddly terrifying condition.
It's a bow and arrow when you have a string.
All right, so in another situation, we could have this energy level, all right? If we have energy E1, then we get a slightly larger loop, like that here. And over here, the same situation. We get a little bit closer because we got more energy to overcome the repulsion of the force, but still we're repelled back out. Poor planning on my part here. Like that. All right, now let's get to the interesting one. The interesting one is the one that's right here going to this critical energy right there. See that? E2. So what happens there is something interesting. We, on the one hand, have a loop like this, but then that goes like this, and this goes like that. And so what's the story here is it goes like this. It's always going to the left below. It always goes to the left below the axis. It always goes to the right above the x-axis because that's the structure here. So this point, depending on the details of like how your particle was situated, if it could either be like coming in and see if it's going into the thing, it might be, what I'm trying to say here is this is an unstable equilibrium. If you just push it a little bit off the equilibrium, you don't know which way it's going to go. So that's it. So, and then one more. Oh, I almost neglected. There's also this guy over here, right? Whee! So it picks up over there, like that. And I think I've got one more color. Better make it count. So this one here, E3. So what that does, and this is where okay, so technically speaking, anytime you're over one of the critical points, you should have like a horizontal tangent for your graph if you're doing it correctly. I never quite achieve this in perfect, like, I try, but, so like it should be like a horizontal tangent there, and it should be a horizontal tangent here, so it's like something like comes up, comes back down, and then it goes through that point. And then it repulses out again. And then it's symmetrically so the other way. Like that. So in short, and then of course you could have an energy level which is above all of these, which would do what? If I have another color. Do I have another color? I think I might have one more color. What's that? The color Gavar, thank you. I got an orange. I found an orange. Up here.
There's no position. It's just non-existent.
Up here, yeah, up here it's not bounded. The motion's not bounded up there. It just does this. It kind of wiggles a little bit, like that, like that. And there's another one down here.
Thank goodness. I would be so sad if it wasn't.
Right. So if you get to energy level E4, the motion is like completely unbounded. It just, you keep going either way. If you're starting to the left, you keep going to the left. You're starting to the right, you keep going to the right. You never bounce back. Anyway, this is what I meant by energy analysis in the course planner, and now you know. So.
Interesting.